So hello and welcome to this video. In this video, we look at the KCSE Physics Paper 1 of the year 2016. KCSE Physics Paper 1 of the year 2016. And let's go straight to the first question. In this first question, it's about branches of physics, where you're told that state what mechanics as a branch of physics deals with. It's a very straightforward question because you get these definitions straight from the course book, and it is the study of motion of bodies under the influence of force. In question number 2, we are told that the figure 1 shows a change in the volume of water in a measuring cylinder when an irregular solid is immersed in it. I forgot to include part of the scale around here because it looks exactly like this. So by the time you download this question paper, I will have made that correction. But I expect you to be able to use a very simple skill of determining the density of this solid, because density is mass divided by volume. To get the volume of this irregularly shaped solid, we need to read the first volume before we immerse the solid, and we subtract that from the second volume after we have immersed the solid. When you are reading the scale of a measuring cylinder, it is important to determine the volume represented by one division on the scale, and we can get that by checking the difference between, for example, when we come here between 160 and 180, we've got 5 divisions, so each division represents 20 divided by 5, and we get 4 centimeters cubed or 4 milliliters. So this should be 84 and this should be 148. So we do 148 minus 84, and when we divide 567 grams by 64, we get 8.86 grams per centimeters cubed. Again, this one was a very simple question. Let's look at question 3. Question 3 is on the oil drop experiment. When a drop of an organic acid of known volume is dropped on the surface of water in a large trough, it spreads to form a large circular patch. State one assumption made when the size of the molecule of the acid is estimated by determining the area of the patch. So we are just required to state one assumption. So I've given you 3. You could state any one of these 3. But remember, when you are taking your exam, when you are asked to state one thing, just state one thing. Don't be generous. So you could state that the patch is 1 molecule thick, or you could say the patch is a perfect circle, or you could even say the molecule is assumed to be spherical. And let's look at question 4. In question 4, we are told that figure 2a and b show capillary tubes inserted in water and mercury respectively. We expect the level to rise in the capillary, but in mercury, the mercury is going to be depressed down. Now, why does this happen? This is a very common question, and you should be able to answer it in terms of cohesive and adhesive forces. In A, the level rises because the adhesive forces between water and glass molecules is greater than the cohesive forces between water molecules. Now, when we talk about adhesive forces and cohesive forces, it's not enough to just talk about adhesive force between water and glass. It is adhesive forces between water molecules and glass particles or glass molecules. So remember to state the force between the particles. So water rises up the tube so that more water molecules can be in contact with the glass. How about in B, in mercury? The force of cohesion within the mercury is greater than the force of adhesion between mercury and glass. And that is why the mercury therefore sinks down the tube to enable mercury molecules to keep together. So over here, the cohesive forces in mercury, or between mercury particles or mercury atoms or mercury molecules, is greater than the cohesive forces, than the adhesive forces between mercury molecules and glass molecules. Let's go look at question 5. We are told that figure 3 shows a hot water bath with metal rods inserted through one of its ends. Some candle wax is fixed at the end of each rod. Use this information to answer questions 5A and 5B. What property of metal could be tested using this setup? Of course, we are talking about this setup here. Of course, this one is conductivity, heat conductivity in solids, or factors which affect heat conductivity in solids. So that is the property that is being investigated, because they have asked us to state the property of metals which could be tested using this setup. We are looking at thermoconductivity and of course factors affecting thermoconductivity in solids. Now, besides the length of the rods that is kept constant, what else could be kept constant when comparing the property for different rods? Over here, when you are investigating how a particular feature affects another feature, it's always important to keep other factors constant. They're asking us what other factors which affect conductivity is kept under control. And one of them is the cross-sectional area of the rods. Look at the rods. All of them have got the same cross-sectional area. So as to make this comparison fair, we keep the rods to have the same cross-sectional area. The other one that we keep constant is the temperature difference between the ends of the rods. And that is why we use this hot water bath, so that the ends of the rods here, all of them are maintained at the same temperature. And then of course the amount of wax that is attached to the rod over there must be the same, because if you attach too much wax, then you find that the force which attaches the wax to the rod would be greater than where the wax is small. So the amount of wax is a factor, and of course how far it is from the edge of the container, how far that wax is. You see, there is a difference between the length of the rod being kept constant and how far the wax is. As a matter of fact, when we talk about the length of the rod, we mean how far the wax is from the edge of the container. Let's look at question 6. In question 6, we are given that figure 4 shows a uniform light bar resting horizontally on the corks floating on water in two beakers, A and B. So this one is just a light cork, and then there is this bar which is being supported by the corks, and since the corks are floating in water, then we put a heater over here. Explain why the bar tilts towards A when equal amounts of heat is applied to each beaker. Why does it tilt? This is about both amounts of water absorbing the same quantity of heat. When that happens, you'll find that because the water on the right is of large amount, we've got many kilograms of water here compared to here, there will be a small rise in temperature here compared to this one, because the amount of heat gained is the same. But the temperature rise depends on the quantity of water which we have there. So over here we are going to experience a small change in temperature, a small rise in temperature compared to here where we have a large change in temperature. So because of that large change in temperature here, the water is going to expand more here, and therefore the density of the water in A will be lower than the density of the water in B. Of course, in both of them, we are going to experience a decrease in density because both volumes of water are going to expand, but A expands more than B, lowering the density in A. That is going to reduce the up thrust on this floater here. So because initially the system was in equilibrium, meaning the amount of water displaced is equal to the up thrust, and the amount of water displaced depends on the density of the water, then you find that when the density of the water is reduced, the upthrust is going to reduce. Therefore, it will not be enough to support this cork as it is. So more water must be displaced. And that is why the cork sinks more in order to compensate for the reduced density. So I've written that answer here. The rise in temperature in B will be less than in A because it has large mass of water. That's the first point. The water in A expands more than in B. So both of them expand, but in A it expands more than in B. Hence, the density of water in A is less than that in B. Upthrust on the cork floating in A is less than upthrust on the cork in B. Hence, the cork sinks more in A in order to compensate for the decrease in density by increasing the volume of the water displaced. Let's look at question 7. Figure 5 shows an aluminium tube tightly stuck in a steel tube. This is the aluminium tube. This is a steel tube. The aluminium tube is inside the steel tube and they are stuck. Explain how the two tubes can be separated by applying a temperature change at the junction given that aluminum expands more than steel for the same temperature rise. Of course, the best way to do this is not to hit the junction, as many students would think, because if you are to hit the junction and aluminum expands more than steel, you find that that factor will make the two even stick with greater force. So the trick is to cool that junction. You could pour some cold water on the junction. If, like for example, you could pour ice cold water or at the junction. Whatever you do, we are trying to cool the junction. Why? Aluminium will contract more than steel, thereby detaching itself from the steel and therefore loosening that joint. You see, if aluminium expands more than steel when heated, if cooled, it will contract more than steel. And let's look at question 8. Question 8a, we are told that an aeroplane is moving horizontally through still air at a uniform speed. It is observed that when the speed of the plane is increased, its height above the ground increases. State the reason for this observation. Of course, this is about the Bernoulli effect, because it's the speed of the plane is increased. The speed of the streamlines above the wings increase, thus lowering the air pressure above the wings. The magnitude of the resultant upward force on the wings increase, causing a rise. And let's look at 8b. We are told that figure 6 shows A, B, and C of a glass tube. State with a reason the part of the tube in which the pressure will be lowest when air is blown through the tube from A towards C. Of course, pressure will be lowest where the cross-section area is smallest, because the speed of the air is highest in this part, making the streamlines much closer to each other, and therefore pressure is reduced. Let's look at question 9. In question 9, we are told that the three springs shown in figure 7 are identical and have negligible weight. The extension produced on the system of springs is 20 centimeters. When you look at this system, you find that these two springs here are supporting a total of 40 newtons. So each one of them is supporting 20 newtons. When you look at the third spring over here, all by itself, it is supporting a force of 20 newtons. So each one of the springs is supporting 20 newtons. And we've been told that as it is, the extension produced by the system of springs is 20 centimeters. That means this part here, which is parallel connection, each one of them stretched by 10 centimeters, and this one too stretched by 10 centimeters, because this one is subject to 20 newtons, so each one of them stretches by 10 centimeters. And this other one here stretched by 10 centimeters. So when you add these 10 centimeters and these 10 centimeters here, that is how you get 20 centimeters. So in order to calculate the spring constant of one of the springs, we just need to consider the force acting on it divided by the extension in meters, and we get 200 newtons per meter. And let's look at question 10. Figure 8 shows two cylinders of different cross-section areas connected with a tube. The cylinders contain an incompressible fluid and are fitted with pistons of cross-section areas 4 and 24 centimeters squared, as shown. Opposing forces P and Q are applied to the pistons such that the pistons do not move. If the pressure on the smaller piston is 5 newtons per centimeter squared, determine force Q. Now, we are told that the pressure in the liquid is 5 newtons per centimeters squared. That means that this is just the hydraulic principle. That pressure must have been exerted by the force P on the smaller area. So when we do force P divided by the smaller area, it should be equal to force Q divided by the bigger area. But the pressure exerted by P, force P on area A, is already given. It is 5 newton per centimeter squared. So we don't need to calculate that by saying P over A1 is equals to Q over A2, because P over A1 is already given as 5. So I would say F1 over A1 is 5 newtons per centimeter squared is equals to F2 over A2, in which case we get Q to be 120 newtons. In question 11, we are told that figure 9 shows a cardboard in the shape of a parallelogram. And a parallelogram is a uniform lamina. That cardboard is a uniform lamina. For uniform lamina, we can be able to determine the center of gravity by geometrical method. In this case, we just need to draw these diagonals, and the point of intersection of the diagonals is the center of gravity. So when you're answering this question, don't just draw lines and leave it like that. Draw the lines, and then where they intersect, name that point COG, or just write the full name, center of gravity. That is what is expected. Let's look at question 12. State why it is easier to separate water into drops than to separate a solid into smaller pieces. Of course, this is about the forces of attraction between the particles in water and the particles in solid. In water, those forces of attraction, which are basically cohesive forces, are weaker than the forces of attraction between particles in solid state. You're just supposed to answer that part that way. Let's look at question 13. In question 13, we are told the graph in figure 10 shows velocity of a car in the first 8 seconds as it accelerates from rest along a straight line. Determine the distance traveled 3 seconds after the start. So up to this point. So we know that when you are given a velocity time graph, we need to calculate the area under the graph. So we can just calculate this area over here all the way up to that point. Would be able to get the area. And the good thing is that since you've been given the grid, you can decide to calculate the area of one small square here, the area of one small square, and then find out how many small squares, complete small squares we have, and then how many half squares we have. You know, that method that we use to calculate area of irregular surface. And when I did that, I got about 72 meters. Section B, question number 14. Question number 14A. Explain why it is advisable to use pressure cooker for cooking at high altitudes. Of course, you know, at high altitudes, the higher one rises above the sea level, the lower the pressure gets. So atmospheric pressure decreases with altitude. Water will boil at a lower temperature, and therefore it will take a long time to cook. This will waste energy, that is the fuel. So what do? We cover that container in order to increase the pressure of the air above the water or above whatever food that we are cooking. So a pressure cooker makes it possible to have high pressure above the water, and because we know that pressure, when we increase the pressure of the air above the liquid, that liquid will boil at a higher temperature. So the food is going to cook at a higher temperature, allowing food to take less time because there is more heat. It will take less time to cook and thereby save fuel. So this question is just about pressure and how it changes with altitude. Remember, it is atmospheric pressure, which decreases with an increase in altitude. Let's look at B. In B, we are told water of mass 3 kg at 20 degrees Celsius is heated in an electric kettle rated 3 kilowatts, that is 3000 kilowatts. The water is heated until it boils at 100 degrees Celsius. Given that the specific capacity of water is this much and heat capacity of the kettle itself is 450, the specific latent heat of vaporization is 2.3 megajoules per kilogram. Determine the heat absorbed by the water. Of course, the heat absorbed by the water will be given by mc delta theta. Delta theta is the rise in temperature of the water, where C is a specific capacity of the water, and I get this value, 756,000 joules. When it comes to the heat absorbed by the kettle, I'll have to multiply the heat capacity by the change in temperature. There is a difference between specific heat capacity, which is in joules per kilogram per Kelvin, and heat capacity. So here I will multiply the heat capacity by change in temperature. Notice that lowercase c is specific capacity, but uppercase c is heat capacity. I get 2700 joules. All this heat is coming from the heater. So when we are asked to calculate the time taken for the water to boil, we know that energy or heat is equals to power times time, and therefore time is equals to the energy divided by power. All that energy required to heat the water, heat the kettle, divide by the power, because it comes from the power of the heater, then is going to give us 4.35 minutes. But you could just stop at 261 seconds. Next, we are asked to how much longer it will take to boil all the water. For the water to boil, we need to know that the heat provided by the heater goes into boiling all of it, mLV. So 300 times T is going to be equal to the mass times the specific latent heat of vaporization, and we get that time to be 28.3 minutes or 2300 seconds. So that question was just as simple as that. Let's look at 15A. State the meaning of the term ideal gas. An ideal gas is a gas which obeys all the gas laws perfectly at all temperatures and pressures. B. The pressure acting on a gas in a cylinder was changed steadily while the temperature of the gas was maintained constant. The value of volume of the gas was measured for various values of pressure. The graph in figure 11 shows the relation between the pressure P and the reciprocal of the volume. Of course, here we are talking about Boyle's law. And this is what we are supposed to get. Suggest how the temperature of the gas could be kept constant. One of the things you will realize is that if you cool a gas, if you compress a gas, if a gas is compressed, that is, you increase the pressure of the gas, you will find that it's probably going to heat up. It's going to become hot. So, but this experiment is supposed to be done at constant temperature. So, how do we keep this temperature constant? There are two methods we could do that. We could change the pressure of the gas very slowly, or after we change the pressure of the gas, we allow it to stand for some time so that it can cool back to room temperature before we measure the new volume. So when the pressure of the gas was changed, before taking the volume of the gas, a time interval of a few minutes would be given in order to allow the gas to cool back to room temperature. Or alternatively, is what we have just agreed, by changing the pressure very slowly. Part 2 of A, given that the relationship between the pressure P1 and the volume V1 of the gas is given by PV is equals to K, where K is a constant, use the graph to determine the value of K. Of course, when we look at the graph plots on the y-axis we've got pressure, on the x-axis we've got 1 over V, and this is what you should always do. When you're given a relationship, whether it is in paper 3 or in the theory papers, always try to see whether that relationship can be expressed in the form of y is equals to mx plus c. In this case, you can see that the graph is a straight line through the origin, so we expect a graph of y is equals to mx, where m is the gradient. And that is why I separated the variables p and 1 over v, so that they are on opposite sides of the equal sign, with the p being on the y-axis, so that the letter or the number which stands out from this variable will represent the gradient, and that is what k does. So k is the gradient of the graph, and the gradient of the graph is given by the change in the value on the y-axis divided by the change in the value on the x-axis, and this is basically what I got. Okay, I had to assume that the volume is in meters cubed, so the inverse will be in per meters cubed. If it was in centimeters, then centimeters cubed, I would, do the same, convert centimeters cubed into meters cubed by dividing by 1 million, something like that. What physical quantity does K represent? Of course, when we look at the units of K, Newton meter, this is work done, and or energy. So the SI unit of K are the same as those of work or energy. So the value of K represents the work done on the gas. Remember, we are compressing the gas, so definitely we are doing work on it. Part 4, suggest one precaution you would take when performing such an experiment. Of course, part of it, we have already talked about it. The gas used must be dry, not wet. And number 2, we would make very small changes in pressure. C of the same question is a calculation which involves Charles' law. A gas occupies a volume of 4,000 liters at a temperature of 37 degrees Celsius and normal atmospheric pressure. Determine the new volume of the gas if it is heated at a constant pressure to a temperature of 67 degrees Celsius. Now, when you are dealing with the calculations in gas laws, there is just one thing to be aware of. The temperature is supposed to be in Kelvin. So the examiner will always give you temperature in degrees Celsius and expect that you should convert that into Kelvin before you substitute. So I've shown you the substitution over here in order to get our V2 to be 4,387 liters. Next is question 16. Define the term velocity ratio for machine. Of course, this is the ratio of the distance moved by the effort to the distance moved by the load. Of course, there is a typing error here. I meant to say the ratio of the distance moved by the effort to the distance moved by the load. Probably I'm going to look at the mark scheme once again in order to remove those errors. 16b, we have this diagram, which is of course the hydraulic press. Figure 12 shows part of a hydraulic press. The plunger is the piston where effort is applied. Over here, this is the plunger, while the ram piston is the piston where the load is applied. Again, there is a typing error there. The plunger has a cross-section area small a meters squared, while the ram piston has a cross-section area capital A meters squared. So the area here is small a, plunger piston of cross-section area small a. I forgot to indicate small a here, while the ram piston has cross-section area capital A over here. And of course, this is oil inside there. We are told that when the plunger moves down a distance d, the ram piston moves a distance capital D. Derive an expression for the velocity ratio in terms of A and small a. Of course, this one is obtained by just realizing that if this one moves through a distance small d like that, this one will move up through a distance d, capital D. What is the same on this side on this side is the fact that, of course, the pressure here is the same as the pressure here according to Pascal's principle. The other thing which is the same is that the volume of the oil that has been displaced by moving this piston downwards is equals to the volume of the oil that has been displaced when this piston moves upwards. So we equate the two volumes. So volume of oil pushed down by plunger is equals to volume of oil pushed or displaced by the ram. Again, here there is another typing error. Volume of oil displaced by the ram or pushed by the ram. Of course, the volume of a cylinder is cross-section area times the height. That's why I get this. So the trick is to get this ratio here, distance moved by the effort to the distance moved by the load, because that is what defines velocity ratio. So when this relationship can be obtained by dividing both sides by capital D and both sides by capital small a, and you find that velocity ratio is A over small a. Part C of the same question is another calculation. A machine of velocity ratio 45 overcomes a load of this much when an effort of this much is given. Of course, this one is quite direct, where we are asked to calculate the mechanical advantage, which is load over effort, which is this value over this value. The efficiency of the machine is mechanical advantage over velocity ratio. Again, the velocity ratio that we've obtained here, the mechanical advantage that we've obtained here divided by the velocity ratio given gives me 74%. That means that the percentage of the work that goes to waste is 100 minus 74, which is 26%. So that question was just as simple as that. Let's look at question 17. When a bus goes round a bend on a flat road, it experiences a centripetal force. State what provides the centripetal force. Again, most of these factors that I'm talking about here, you find that I've explained them extensively in different videos. That is why when I prompt you to download the question paper and then click on various concepts, you find that I've chosen about 50 videos which are going to be very useful. If you can watch some of them, it will really help you to understand these concepts. So, like for instance here, I'm talking about circular motion. There is a full video about concepts in circular motion that I have included at the end of that paper as a link. Just click on the link and you'll be able to understand all these factors that we are talking about here. So what provides the centripetal force? Of course, it is a sideways frictional force on the tires by the road surface. Remember to state that word, sideways frictional force. Right. Part B, state the purpose of banking roads at bends. You find that if a road is not banked, then all the centripetal force will be provided by the frictional force between the tire and the road surface. Now, many things could happen, such as on a wet road, the friction force is reduced, and you find that the turning, or it may not, the friction force developed may not be enough to provide the required friction force. In such a case, the car is going to skid and probably there will be an accident. So in order to avoid reliance on the sideways friction force between the tire and the road providing the centripetal force, we bank the roads so that we can have, let me just explain this using this sketch here. This is the angle of banking of the road. If this is the car, you'll find that there are several forces which are acting on the car. One of them is the weight of the car downwards, and then perpendicular to the surface, to the road, there will be this component of the weight of the car, because this one will be theta, this one will be mg. This component of the weight is mg cos theta, and then the reaction force here is now at an angle. So because the reaction force is at an angle, that reaction can now be resolved towards the center of the circular path. So you see that the component of this reaction, which is towards the center of the circular path, comes in to increase the amount of centripetal force in addition to the sideways friction force. So that is what we mean by saying that the horizontal component of the reaction provides the centripetal force. So let's continue. So by having a component of the normal reaction which acts horizontally in order to provide the centripetal force. Of course, you can have the two of them, friction force and the horizontal component of the normal reaction, providing the centripetal force. The idea here is to reduce reliance on friction force only. C. A student whirls a stone of mass 0.2 kilograms tied to a string of length 0.4 meters in a vertical plane at a constant speed of 2 revolutions per second. State two forces acting on the stone when it is at the highest point. Again, in another video that I've given at the end of that download, you would be able to understand the concept of the vertical circle. I've dealt with this concept extensively, so don't fail to go to those videos in order to refresh your knowledge when you look at vertical circle. So the two forces which are acting on this stone at the topmost part of the circle will be the weight of the stone and the tension in the string. Of course, the angular velocity of the stone will be given by the angular displacement divided by time, and time is 1 second, and this object makes 2 revolutions per second. 1 revolution is 2 pi radians, so since there are 2, that's why there is these 2 here. 2 times the number of angles in radians in a complete revolution, and then when you divide by 1, you get 12.56 radians per second. Part 2, the tension in the string when the stone is at the highest point. We know that centripetal force is provided by mg plus, I think this part here may not be quite correct. This one may not be quite correct. Let me correct that. This is at the top of the circular path. This is the mass. There will be tension in the string. There is its weight, mg. And because both of them are pointing downwards, they are going to provide the centripetal force. So centripetal force is mg plus t. Centripetal force is given by m/r omega squared is equals to mg plus t, and t is equals to m/r omega squared minus mg. So instead of adding the 2 newtons, I should subtract the 2 newtons. Let's go back to the answer that I've given in order to make those corrections. So over here, we are supposed to subtract 2 from this value here. And when we subtract 2, we get 10.64. So it is not this value, but it is as I've shown there previously. And let's go to question 18. State Newton's first law of motion. The rate of change of momentum of an object is directly proportional to the resultant external force acting on it and takes place in the direction of the force. So such a law is quite direct. Then there is part B, where we are given a wooden block resting on a horizontal bench, being given an initial velocity u so that it slides on the bench surface for a distance d before coming to a stop. The values of d were measured and recorded for various values of initial velocity. Figure 13 shows the graph of u squared against d squared. And here we've got the graph. We are required to determine the slope of the graph. Of course, you can take the largest square or right-angled triangle, in which case you just need to read this value, and this value. That is what I did. I got 6.7 meters per second squared. Why meters per second squared? This is meters squared per second squared. When I divide by meters, I get meters per second squared, which is some kind of acceleration. After that, we are told that given that u squared is equals to 20 kd, again, you can see that u squared is on the y-axis and d is on the x-axis. So by separating the variables, we are supposed to see that the gradient that we have just worked out is equals to 20k, in which case now the value of k can be worked out by, we know the slope is 6.7, so this is supposed to be k. This one here, it's not s, because when we substitute the value of s as 6.7 is equals to 20k, then k is going to be equal to 6.7 divided by 20. So this is k, which I got as 0.335, again meters per second squared, because this 20 is just a number. So the units of k will be equal to the units of the slope, which is of course the units of acceleration. And the last part here is about a car of mass 800 kg. It starts from rest and accelerates at 1.2 meters per second square. Determine its momentum after it has moved 400 meters from the starting point. The moment I'm asked to determine the momentum of an object, I know I need its velocity. So by using these other details, it starts from rest, and this is the acceleration. I need to, and this is the displacement that it covers. I need to get the final velocity, and I can do that by using an equation that does not have time, and it happens to be this equation here. So this equation allows me to calculate the final velocity of the object, in which case now I can use that final velocity to calculate its momentum, because we are asked to determine its momentum after it has moved 400 meters. So the velocity I use is the velocity it has finally after covering a displacement of 400 meters, which I've worked out. And when I multiply the two, I get this value, kilograms meter per second. And that is the last question in this paper. So go right ahead, download the whole question paper. These are the links that I was talking about. There are many, and I'm continuously upgrading this list. Each and every time I prepare something new, I put it in this list. So don't forget to go to these videos. When you look at these videos, some of them are very detailed on a specific topic. Some of them are just on complete past papers. Others are in a complete topic. Others is just a simple concept in the study of KCSE physics. So I would consider these links to be very useful. So go right ahead, download the question paper in the video description, and first of all, work out the questions in this paper, which is the 2016 paper. And then after that, you replay this video so that you can see how the answers were obtained. After that, you can go and play these videos here where I teach you more concepts in physics. And of course, don't forget that when you are playing these videos, you can go to the scroll bar of the video where you find that I've given you timestamps on every video, showing you that you can skip to a particular question when you are dealing with that. Let me just show you briefly what I mean by that. So this is what I mean by timestamps. If you run the cursor along the scroll bar here, you can see as I run along it, you can see questions are popping up. This is question 5. I got question 6. I got question 7. I can click, for example, here I'm talking about question 14 part B. If you just click this one here, the video jumps to that particular question, and you find that this one is a neat way of showing you how you can be able to skip to the question of your choice. For example, you don't have to, if you have already played the whole video all the way up to the end, and then you want to review a particular question, I've made it very simple. These timestamps are going to be very useful. Click on any one of them. It will take you to the question of your choice. And let's stop at that point, hoping that you're going to share this video with your friends, because that is how we grow. Until next time, continue revising hard, and I continue to wish you all the best. In the next video, I'm going to look at another paper altogether.